Ma'am,
Yes.
ma'am, the quotient is 2 and the remainder is 0.
Remainder is 0 and quotient is, just a second. Ah, yes, 2. By mistake, we have written 1. Yeah, it is 2. Correct. So we had started with the question 43 divided by 23. So we had dividend as 43 and divisor as 23. So we had written the question of quotient as binary of 43, 10
Ma'am, 46.
sorry, 46. Then we had converted the divisor 23 into its binary. So M was 00 10111 minus M was 2's complement of M, which was 11010001. So after we completed first cycle, the result was in AC 11011010, and in quotient the result was 01100. Check with your answers. Then after that, after completing second cycle, since the result of your AC was negative, so we had perform left shift and we performed AC is equal to AC plus M. So final result was 11010011 and the contents of Q were 111000. Again, since the value of AC was negative, so we did left shift and we performed AC is equal to AC plus M. Again, the value was negative, so we have substituted the value of Q0 as 0. So the contents of AC was 110110 and the contents of Q were 11 and 4 times 0. Again, the result of AC was negative, so we did left shift first and then we performed AC is equal to AC plus M. Now to substitute the value of Q0, we again checked that AC was negative, so we have added the value of Q0 as 0. So the final result of your fourth cycle, the contents of AC was 110100 and the contents of Q were 1 and 5 times 0. Then again, the value of AC was negative. So we did left shift first and then we performed AC is equal to AC plus M. But here we observed that the content of AC after doing AC is equal to AC plus M was found positive. So we have substituted the value of Q0 as 1. So the result of fifth cycle was all the contents of AC were 0 and the contents of Q were 5, 0 and 1. Now, in the result of fifth cycle, the AC was observed to be positive. So we did left shift first and then we performed AC is equal to AC minus M. So the result of AC is equal to AC minus M. The result of AC was negative. So we substituted 0 at the value of Q0. Now again, the result of your sixth cycle was 11010001 and the result of Q was 4 times 0 and 1 0. Since we are supposed to stop here, but the result of AC is still negative, so we have to perform the resultant cycle where we have to do AC is equal to AC plus M. So we get a final result as AC as all zeros and Q as 0000010. So our remainder is nothing but the contents of AC, which is 0, and our quotient is the contents of Q, which is 2. By mistake I have written it 1, it should be 2. So when I divide 43 with 23, I get my remainder as 0 and I get my quotient as 2. Is this result correct with every one of you?
Yes, ma'am.
Okay. So we begin with the next topic now. That is IEEE 754 standard. Last topic of this chapter. After this, whatever algorithms are there, I have already told you that we won't be covering that. Okay. Now, what is this IEEE 754 standard? This standard addresses many problems which were found in floating point implementation. Now, if you remember in the beginning of the chapter, we had done two types of data representation. One was the fixed point representation and the second was floating point representation. If you remember, the format of floating point representation was something like this: m into b raised to e, where m was mantissa, b was our base, that is biased, and e was the exponent. So I had given you one question where it was asked to you to identify what is m, what is your biased, and what is your exponent. But if we follow that floating point representation, we were not getting the actual result for whichever number was given as input. So to avoid that problem or to avoid that difficulties, we started using this IEEE 754 standard. Now what does this IEEE 754 standard says? That it is represented by using three components. Here also we have three components, that is mantissa, biased and exponent. Here in IEEE also we'll be having three components. Which are those three components? First one is the sign of mantissa, which can be either be 0 or which will be either 1. That is nothing but the sign magnitude. So if it is 0, that means the number is positive. If it is 1, that means the number is negative. Or if the number is positive, we have to substitute 0. Or if the number is negative, we have to substitute 1. Where in the first component, and what does that first component say? That it is nothing but the sign of mantissa, that is nothing but the sign magnitude. Okay. Next is the bias exponent. Now what is this bias exponent? The exponent field needs to be represent both the positive and negative number. So this field will represent two numbers, which can be either positive number or negative number. Okay. A bias is added to an actual exponent in order to get the stored exponent. Now what does this mean? In IEEE, we have two type of representation, a single precision representation and a double precision representation. What are these both? We'll be seeing in the slides ahead. But for now, just remember, for this bias exponent field, we have two types of IEEE 754 precision. One is single and one is double. So for single, this bias exponent value is 127 and it is fixed. I repeat, for bias exponent, if IEEE is single precision, the value is 127. And if this biased exponent is double precision, the value is 1023. Okay. Now what we have to do is with these two values, if it is single precision, whatever exponent value we get here, we have to either add that value to 127 or subtract that value to 127, depending upon whether the exponent is positive or negative. Okay. If it is positive, we will add. If it is negative, we will subtract. By whom we have to add and subtract? We have to add and subtract with 127 if it is single precision. Okay. Now, if it is double precision, we have to add that exponent or subtract that exponent with the value 1023. Okay. Again, if it is positive, we will add it with 1023. If it is negative, we will subtract it with 1023. And whatever value we get after addition and subtraction, that value is converted into binary and it is called as biased exponent. Okay, this will get clear when we solve one sum. So for now, just remember, if it is single precision, the bias exponent is 127. So we either add or we subtract depending upon the exponent value. If my biased exponent is double precision, my value is 1023. And then we either add or subtract those exponent value. Whatever resultant value we get, we convert it into the binary. Okay. Next is normalized mantissa. Now what is this normalized mantissa? The mantissa is a part of a number in scientific notation or floating point number consisting of its significant digits. So whatever number is there in the question, we convert that number into a floating point number. That is, we first convert into binary, then we represent it into floating point, and whatever value we get, that value is considered to be as normalized mantissa. Okay. So instead of having this M, B, and E in floating point, my IEEE will be having a signed magnitude, a biased exponent, and a normalized mantissa. All this three representation can be in the form of single precision or it will be in the form of a double precision. So let us first see the single precision. So if it is single precision, all these three will be represented into how many bits? 32 bits. Okay. So if it is single precision, this is the format. And the format has how many bits in total? 32 bits in total. Okay. Where my first is the sign magnitude, which was this part. Second is the biased exponent, 8 bits, which is this part. And the third is the 23 bits of mantissa, which is nothing but the floating point representation, also called as normalized mantissa. Okay. So 1 bit for sign magnitude, 8 bits for biased exponent, and remaining 23 bits, which is nothing but the normalized mantissa or the floating point representation. So when I add this 1 plus 8 plus 23, I get 32 bits of representation. And that 32 bit of representation is called as single precision. Okay. Now we have one more precision called as double precision. What is the difference? All these three fields will remain same. Only these 32 bits will get converted into 64 bits, where my 1 bit is reserved for sign magnitude. 11 bits are represented by this biased component, and remaining 52 bits are represented with this floating point representation. Okay, so if you see 1 plus 11 plus 52, I get 64 bits, which is double precision. So your IEEE format is divided into two: single precision of 32 bits, double precision of 64 bits, which individually has sign magnitude representation, bias exponent representation, and normalized mantissa representation. Is this understood up till here?
Yes, ma'am.
Everyone?
Yes, ma'am.
Okay. So let us look into the example now. So if it is single precision, I have 32 bits, out of which 1 bit is for sign, 8 bit is biased exponent, remaining 23 bits is normalized mantissa, and my biasing value is 127, as I just said. If it is double precision, 1 bit is for sign, 11 bits are for biased exponent, 52 bits are for normalized mantissa, and my biasing value is 1023. So from 0 to value 0 to 22, that is LSB to MSB, 0 to 22 is mantissa, 23 to 30 is bias exponent, and the 31st bit is the sign magnitude. For double precision, from LSB, 0 to 51 are reserved for normalized mantissa, 52 to 62 are stored for biased exponent, and the 63rd bit represents the signed magnitude. Okay. Single precision biasing value is 127. Double precision biasing value is 1023. Okay. Now let us look at the example. So we have a question that 178.1875, that is this decimal value, has to be represented in single floating point format and double floating point format using IEEE 754. Okay. Understand the question? What we have to do is, in this question is, we have a decimal number, and this decimal number has to be represented in an IEEE 754 format. So when it is said IEEE 754 format, means it includes single precision as well as double precision. So we know if it is single precision, we have to represent it in 32 bits, and if it is double precision, we have to represent it in 64 bits. In both the format, we have sign magnitude, we have biased exponent, and we have normalized mantissa. Okay. So now to execute or to perform this, we have total 3 steps. What is the first step? We convert the given decimal into binary. Second step is we perform a scientific notation, or we represent the number in scientific notation. And the third format is, or the third step is, we either use single precision if it is as single precision, or we use double precision if it is as double precision. If it is as both, then in step 3 we have to perform single and we have to perform double. Is this 3 steps clear to you? Let it be any decimal values. For every decimal values, you have to perform 3 steps. First step is convert the given decimal into binary. Second is represent that binary into scientific notation. And third step is put it in either single precision format, which is this, or double precision format, which is this. If it is not as single or double, you will have to represent it in both the format. Now let us see how do we start solving. So our question number is 178.1875. So what do we do is, we will first convert 178 into binary. So do we know how to convert 178 into binary? Yes, we divide the number by 2 until we get the remainder as 0 or quotient as 1. Okay, so when I convert 178 into binary, what do I get is 10110010. So this number 10110010 is nothing but the binary of 178. Understood up till here?
Yes, ma'am.
Okay.
Yes,
Now
ma'am.
next is you have to convert 0.1875 also into binary. So whatever we have in this floating point, and if we want to convert it into binary, what do we do is we multiply it with 2. Yes or no? This might have been done into your digital. Decimal
Yes,
के
ma'am.
बाद जो भी number है,
Yes,
if I
ma'am.
want to convert that number into binary, you have to multiply it by 2. So when I multiply when I multiply 0.1875 into 2, what do I get is 0.375. Again, what I will do, I will take this 0.375 and multiply it with 2. What do I get? 0.75. Again, multiply 0.75 into 2. What do I get? 1.5. Again, multiply 0.5 into 2, we get 1. So up till when we have to do this? Until we get 1, or if we get this same value as repeating. Yes or no? Are you aware of this? Yes or no?
Yes.
So when are we
Yes, ma'am.
supposed to continue this until we get 1 as a result, or if we get the same repeating values coming, we have to stop there. So how do I take a binary of this? Whatever comes before this decimal point, 0011, I will write it separately, that is 0011. So what is the binary of 0.1875? The binary of 0.1875 is nothing but 0011. Is this understood up till here?
Yes, ma'am.
Okay. So I have a decimal converted into binary of 178. I have decimal 0.1875 converted into binary, which is 0011. So what will I do now? I will write it together. How do I write it? My number was 178.1875. I have converted this decimal into binary, that is 178 ka binary I have written over here. I have put this decimal as it is, and whatever is the binary of 1875 I have kept as it is, that is 0011. Again, if you keep on doing, you will get the same value 0011. Again, if you keep on doing, it will give you value 0011. So this keeps on recurring, therefore I have written dot 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 over here. Okay, so I have completed my first step, which is converting this number 178.1875 into binary. Understood the step 1?
Ma'am,
Huh.
ma'am, how does it keep on recurring? I didn't get it.
Yeah, you have to stop at 1. So when you stop at 1, the value keeps on repeating. Or you have to do until you get this 0.1875 as it is. So since I have got 1, I have stopped and I have assumed that following values will be same. Or if you do not want to keep this recurring, if you do 0.1 into 2, whatever answer you get, you append that value over here.
Ma'am, but it is only zero, na? If we multiply zero with two, we will get zeros only.
If it is 1, what do we assume that it is? We have to stop there.
1.0.
We have to stop there, and we have to keep this value repeating. That is what I'm telling. It is, the flow is like this. If you stop at 1, keep repeating the values, or else you keep on multiplying till you get this values as recurring. Or if you do not want to keep this values recurring, only write 0011. That is also correct. Is this understood?
Okay,
Am I audible? See, there are 3 things. Either you keep on multiplying till you get 0.1875 as it is. Second, you stop when you get 1 and assume that remaining bits are also repeating. Or else whatever you have got like 0011, stop there. Why I am telling you to keep repeating this? Because we have to represent this numbers either in 23 bits or in 52 bits. Okay. So therefore I am telling you to keep repeating that values. Now what is step 2? Represent the above binary, that is this binary, into a scientific notation. So how do you do scientific notation? we shift the decimal to the left until the first number. So what is my value before decimal? It is 10110010. That is nothing but this. I have copied it as it is. Okay. Followed to that, I have a decimal point. Now what I have to do is I have to convert this into a scientific notation. So to convert into scientific notation, what do? Is I will keep on shifting left until where? Until I have reached the first number. Okay. So just count how many shifts I have done. 1, 2, 3, 4, 5, 6 and 7. So what is the value after I shift? The value is 7. So I have written that value as it is. Now what I have to do with this value 7 is I have to multiply the factor with 2 raised to 7. Why this 7? Because I have shifted with the 7 bits. So I will multiply it with the factor 2 raised to 7. Suppose if I have shifted it with 5, I will multiply with the factor 2 raised to 5. If I have shifted with 3, I will multiply with the factor 2 raised to 3. Okay. So what I have done is I have shifted the 7 bits to the left. So my decimal has now shifted over here. 1 point, and all the remaining bits are now shifted after the decimal. So they are converted into floating point now. So if you see this 0, 11, 00, 10, that is 0, 11, 00, 10 are now shifted after the decimal and converted into floating point. After that, which are the values? The values of my 0.1875, that is 0011, 0011, 0011, keep on repeating. Multiply with what factor? The factor that I have got over here. What is that factor? 2 raised to 7. So this is your scientific representation. How I have achieved that? I have copied this decimal as it is, shifted that decimal up till I reach the first value, counted the total number of shift, multiplied it with the total factors, shifted my decimal to the first position, and remaining all values of the binary will be considered as the floating point. Understood up till here? Yes or no? Is it understood? Okay.
Yes, ma'am.
Now what is step 3?
Yes, ma'am.
Represent it in IEEE format. So we'll first see how to represent it in single precision. So how is single precision format? 1 bit for sign, 8 bit for biased exponent, 23 bits for mantissa. Now what is the number? The number is 178. Is it positive or negative number? Positive. So what will be my sign magnitude? My sign magnitude will be 0. Now I have to calculate a bias exponent, which should be of how many bits? 8 bits. So to calculate this bias exponent, I know that bias value for single precision is how much? For single precision, the bias value is 127. So what I will take? I will take that 127. And what I will write? That the bias exponent is 127 if it is single precision. Now, if you remember, I have told you that it can be either a positive number or a negative number. If it is positive, we will add to the bias value. If it is negative, we will subtract with the bias value. So what is that number? The number I have got in the step 2 is 7. So is this a positive or a negative number? A positive number. So what I have to do with this positive number is I have to add it with the bias value. So I will add 127 plus 7. From where did I get 127? That is a bias value. This 7 was the exponent which I got from the scientific notation. And when I add 127 with 7, I get a value 134. Now what I have to do with this 134 is I have to convert it into binary. So the binary conversion of 134 is 100001110. So I have represented my bias exponent into 8 bits, which is nothing but 134. What is my mantissa? My mantissa is nothing but all these bits after the decimal. So all these bits after decimal are copied as it is over here. So I have represented 178.1875 into a single precision, which is sign magnitude as 0. biased exponent is 134, and mantissa, which is calculated from step number 2, which is all the binary numbers after the decimal. Yes or no?
Ma'am, from where did we get that 127?
127, it is fixed. For single precision, bias is 127. For double precision, bias is 1023. I have not got it from anywhere. The concept says that if it is single precision, the bias value has to be taken 127. And if it is double precision, the bias value has to be 1023.
Okay, ma'am. Clear.
Okay. Now I have represented in single precision. Similarly, I will represent it in double precision also. What is the format? First bit should be sign magnitude. Second is the biased exponent of 11 bits. Remaining 52 bits are mantissa. So do I know what is my mantissa? Yes, my mantissa is already this value, which is calculated from step 2. What will be my sign magnitude? Check the original decimal number. Is it positive or negative? Positive. So my sign will be 0. My mantissa will be all the values after the decimal from step number 2. Now only remaining thing I have to calculate is a biased exponent. Now I know what is the bias value for double precision. What is the bias value for double precision? 1023. I have to add that 1023 with my exponent value. What is my exponent value? 7, which I have calculated from step number 2. So is it positive? Yes, it is positive. So if it is positive, what I have to do is I have to add with 1023. So when I add 1023 with 7, what do I get is 1030. What I have to do with this 1030 is convert into binary. So binary of 1030 is 1000000001110. So sign 0, bias exponent is binary of 1030, which is this, and mantissa, which is nothing but taken from step number 2, all these values. So this is how you represent your double precision. So only difference in both is here your bias value is 127 and here your bias value is 1023. Is this understood up till here?
Yes, ma'am.
Yes. So
Yes.
if I give you the number, can you convert that number into IEEE single precision and double precision format? Yes or no?
Yes, ma'am.
What are the 3 steps that you have to remember? First step is convert that given number into binary. Second, represent it into scientific notation and find out the exponent value. In the third step, if it is single precision and if the number is positive, add it with 127. If it is double precision, add it with 1023. But if from the bias exponent, if you have got the value negative, you will subtract it from 1023, or you will subtract it with 127. Okay. How do we write this IEEE format? This IEEE format is written as 1 into n into 2 raised to e. Okay. Now, how do you write this 2 raised to e? It will be either 127 or 1023. When it will be 127 when it is single precision. When it will be 1023 when it is double precision. So what do we do is, e is nothing but the exponent. Okay. So what do we do is, even if we get e as negative, we convert it into a positive number. So what do we do is, we have equal to e minus 127. That is this, e minus 127. So if I want to bring e at this side, that is on the left hand side, what do I do is, e equal to 127 plus the exponent value. So for this example, my exponent was 7. So what did I do? 127 plus 7 equal to 134. And for double precision, what did I do? I took e this side. So I got 1023 plus the exponent value 7. So I got 1030. Okay, so how do I represent it? 1 into n 2 raised to e. And what do you write for e is, if it is single precision, you write e minus 127. And if it is double precision, you write e minus 1023. And you calculate that e from step number 2 and represent the bias exponent either by adding or by subtracting. Is this clear up till here?
Ma'am, when do we have to use this?
You You don't have to use this, you just have to write this. Only this much has to be written up till here. This is just with respect to our example. If you want that how did I calculate this, it is this how it is, this is the way I have calculated by writing this. So you don't have to write this, you just have to mention over here in the theory part that instead of using m into b raised to e, IEEE uses the format or the representation which is 1.n into 2 raised to e. Understood?
Yes, ma'am. Clear.
Okay. So is this topic understood? IEEE 754 representation.
Yes, ma'am.
Okay.
Yes, ma'am.
Now what, we have one more question. Now what is going to happen is in the final exam, you will not get any sums on this. You will be getting a theory part. But what you have to write in theory is, I will be telling you now. You will write that IEEE 754 format was being used because we were not getting the appropriate result from floating point representation, which was m into b raised to e. So we started using IEEE format, which says that you have to make use of 1 into n raised to 2, 1 into n into 2 raised to e. This IEEE format has the three components for the representation. You will be explaining these three representation components. You have two formats, the single precision and the double precision. You will be explaining this single precision, 32 bits, like how you get sine, how you get exponent, how you get mantissa. You will be explaining the double precision, how you get single, how you get sine, how you get exponent, and how you get mantissa. The number of bits for both will be different. You will be explaining that. And followed by that, you will also tell what is the bias value for single precision, what is the bias value for double precision. Followed by that, you will give an example for any such question in your exam. You will be explaining the example if the question comes for 8 marks. But if the question is only for 4 marks, no need to explain the example. Just explain up till this slide with this 3 steps. Step 1, convert into binary. Step 2, find the scientific notation. Step 3, represent it in single format or represent it in double format. But if it comes for 8 marks, you have to explain with solving this example. Am I clear?
Yes, ma'am.
Yes, ma'am.
So in exam, there will be theory on IEEE, but if it is asked for 8 marks, you have to explain with the example. So if it is for 4 marks, no need to explain, but if it is for 8 marks, you have to explain. And even if a sum is asked, say suppose external का question paper है, अगर उसने question पूछा है, solve करो, so you know how you are supposed to solve. Okay. Now take this as a homework. Represent this number 263.3 in single precision as well as in double precision. Write down the question. Represent a number 263.3 in single precision and double precision using IEEE 754 standard. Can you all do this? Yes or no?
Yes, ma'am.
What
Yes,
we have
ma'am.
done in step 1, convert 263 into binary. So binary of 263 is written over here. Convert 0.3 also into binary. So 0.3 into binary is 0, 1, 0, 0, 1, 0. Sorry, 1, 1, 0, 1, 1 keeps on repeating. So after I get the final result, this is the binary of 263.3. Then what do we do in scientific notation? We shift the decimal until we reach the first number. Count those many numbers. Whatever number we get, we consider that as a exponent. So values we have shifted with total 8. Therefore, I have multiplied with the factor 2 raised to 8. In step 3, we will represent it in single precision. So what do we do is the bias value is 127. What is our exponent value? It is 8. Since it is positive 8, so we do 127 plus 8. What do we get is 135. So first bit is sign magnitude. Since the number is positive, so we put 0. Second 8 bits is biased exponent, which will be 135, the binary of 135. And the remaining is mantissa. From where I have taken this mantissa? From the step 2, which is all the numbers after the decimal. Clear? How will you do this in double precision? Only change will be 1023 plus 8. Correct?
Yes, ma'am.
Okay, so
Yes,
what you
ma'am.
will get? 1031. So you will represent 1031 into binary and replace this value with that 1031. Remaining sign and mantissa will remain same. Clear? Yes or no?
Yes, ma'am.
So you will do this as a homework and we will discuss the answer of double precision and we will verify with the answer of single precision from the PPT. Okay. So with this we have completed with chapter 2.